Hi, and welcome back to Cluster Rant. My name is Doug Edline, and I'm the Senior HPC Editor at Linux Magazine. And today we're going to talk about Amdahl's Law. So, before I get started, make a little note. Some of the friends of mine who viewed my previous videos suggested that I wear black because it makes me look thinner. So they got me this t-shirt. And I hope it works. So now, getting back to our lesson today. So, Amdahl's Law, what I like to call the bucket of cold water that gets thrown on most people that are new to parallel computing. There's this notion that all I have to do is keep adding processors to my problem and it's going to get faster no matter what. That is actually not correct. So, Amdahl's Law is a way we kind of quantify that. Now, I know what you're thinking. Math! Ooh, math. Okay, so I'm going to go through this mathematically for the three of you out there that are not mathematically challenged. And then in the second part of this video, I'm going to present this in a completely kind of simpler way. And we'll get to that in the next part of the video. But for those of you that can do arithmetic and a little bit of math, let's go through this real quick. Amdahl's Law. Gene Amdahl, computer designer, put this together when people were starting to look at parallel computing a long time ago, back in the early days. So parallel computing is not an idea that popped up with Beowulf clusters, though some people think it is. It did. It's a way to talk about what you can expect from parallel computing. Now, we have this equation that reads like this. The speed up you can expect equals 1 over 1 minus p plus p over n, where n is the number of parallel parts and p is the parallel portion of the program, the percentage of the program. A few things to notice about this. Well, first, programs can be divided into two separate areas. Those that must be executed in a sequential fashion, bing, 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 right after one and one right after another. And then concurrently, those pieces that can be executed in a concurrent fashion, and if it makes sense, run them in parallel. And we'll learn a little. Amdahl's Law has a little bit to say about running things in parallel. So, what it's saying is, what Amdahl's Law is saying is the speed up you can expect depends upon two major issues. One is P, the proportion of parallelism in your program, or concurrency, and the number of processors, or cores, what we want to call them, n. Interesting thing. First, 1 minus p is essentially the sequential piece. So what it's saying is the sequential piece, 1 minus p, plus the parallel piece, if n is one processor, is just running the program on one processor. So that's one end of the law. What happens, however, is it tells us when we start making n bigger and bigger and bigger. And if we solve this program for various values of p, well, for a single value of p, sorry, and various values of n, we always get a curve that looks like this, which is a diminishing return, which says at some point things are not going to speed up any faster than the sequential portion. Why? Because as n gets bigger, this stays the same, this term gets smaller and smaller, and in the limit it goes to 0. I don't want to scare you with the math there. So, pretty much every program that you try to run in parallel is going to behave like this little chart here. The speed up and n are going to depend on your program. But at some point, it's not going to go any faster. And that's the point. That's why I call it the bucket of cold water that gets thrown on a lot of people who start out in parallel computing because they think, I'm just going to throw 100 processors in my problem and it's going to go faster. And guess what? Boo-hoo, it doesn't. And this is probably why. So, in the next part of this video, part 2, we're going to take a look at something I call the lawnmower law, which isn't Amdahl's law, is not as nice and elegant, but it gets the point across as well. So, with that, tune in for the next video and you'll get the other side of this law that pretty much will help you understand the limits of parallel computing. See you then.